Welcome. In this lecture topic, we'll be addressing something called query optimization. Recall from our examination of SQL that we had indicated SQL is a non-procedural language. Even when we're working with multi-table operations, performing joins or subqueries, we really do not tell the system how to get the answer. We basically are describing what the content will look like, and then we leave it up to the system to determine how to produce that result for us. The magic element that accomplishes this is something called the query optimizer. Through this lecture topic, we'll gain some insight to what query optimization is all about and explore some of the metadata that is typically used by the query optimizer in arriving at its execution plan, the strategy for producing the desired output to satisfy our query's objective. As we've noted, SQL is a non-procedural language. This means that users specify the data content that they want to be contained within the result. They do not specify how the data will actually be accessed and retrieved from the database. There's a special component within a relational database called the query optimizer that makes the decisions as to how the data will be accessed. The optimizer is analogous to an expert system. If we have a human programmer who is well aware of the data distribution and data organization, that programmer could make very informed decisions as to when to perform a certain type of operation versus another operation. This is the idea of what has been captured or encapsulated within the optimizer. An available approach for accessing and retrieving data is called an access method or an access path. We'll examine some different access methods that are available with respect to the structures for data stored within a relational database. When we assemble all of the steps to process a single SQL statement, this is referred to as an execution plan. We'll show you how you can obtain information about the execution plan used or generated by the query optimizer. To provide you with a basic explanation of the role played by the query optimizer, we'll consider a simple task. Using this task, we'll present general concepts that relate to access paths and execution plans. Assume you were asked to find an explanation of the term query optimization within a database textbook. There are two practical approaches that you could follow. A sequential scan, where you would read every page in the book looking for that phrase, query optimization, and then note those pages where this phrase was observed. An index scan, where we search the index for the book to find the pages which have information about query optimization, and then we read just those pages. As we present the general data structures used by database systems, we will examine these two approaches in some detail. We will now provide a basic introduction to a data structure called a B tree. For those interested in greater detail, refer to the paper by Douglas Comer, noted in the references at the end of the presentation. For a transactional database or an OLTP database, some variation of a B tree, whether it be an actual B tree, B star, B plus, whatever, is used for index storage. A B tree is said to be a height-balanced tree. This means that any record retrieved through the index or any data retrieved through the index requires the same amount of time to access. The distance from the root to any of the leaf nodes is the same because it's height-balanced. In general, a form of a B tree provides good performance for small and large tables. for different ways of access. An access method that involves what's called a matching index scan, or alternatively, an access method that involves a range scan. Indexes are used in database systems and also for file systems. Blocks of a B+ tree are generally maintained at about 3/4 of their capacity. They're about 3/4 full. This allows new values to be inserted without any growth in the index. This is quite different than simple tree structures that you may have seen in a basic data structures course, such as a binary tree. When a block in a B+ tree reaches its capacity, the block will split. And as the tree grows, new blocks eventually will be added, and it will require the creation of many new blocks before the height of the tree is actually affected by this growth. When the tree does grow in height, it grows upward rather than downward, as you're probably acquainted for the growth of a binary tree. Here's a very simple illustration of a B+ tree. Note that in practice, each node of a B tree will contain many keys and many pointers. Here, we're just giving you the feel for what the tree looks like, and we'll be able to explain the access methods for manipulating or working with the content of an index. The lowest level of the index contains what are called leaf blocks. These blocks store every indexed value together with a pointer to the table that contains this value. Thus, we're talking about two structures. The index itself is one structure, and the table that contains the complete rows or records represents a second structure. But the two structures are related, as we're suggesting here, by the pointers contained within the leaf blocks of this B tree. The leaf blocks themselves are also linked for sequential scanning. Notice the horizontal pointers between these leaf blocks. So effectively, you have a hierarchical structure on top of a linear or sequential structure. This constitutes the B tree, or in this case, the B+ tree. And again, remember, this overall structure is different and distinct from the table. So note that each block in the tree corresponds to an actual block in the database. What that means is it's a physical record. So if your database block size is 4K, then that's how big these nodes would be. If your database block size was 8K, that would be the size of the nodes within your index. Let's look at characteristics of this tree, observing its content. Notice the block that contains the value of P. This is the root of the tree. The blocks that contain the horizontal pointers, such as D, HL, N, and so forth, are referred to as the leaf blocks or leaf nodes within a tree. Blocks above the leaf nodes have these vertical pointers in our diagram. They're pointing downward. These are called branch nodes or branching nodes. So the branching node with keys H and N contain 3 pointers. Again, this is a very simplified illustration. Remember that if our block size was actually 8K, we would have much more than just 2 keys, many more keys, many more pointers. But the block that contains H and N, that branching node, has 3 pointers. The leftmost pointer identifies the path to follow, moving from top to bottom, going downward toward the leaf nodes. When the value that we're searching for is less than H. The middle pointer identifies the path to follow once we've reached this branch node for values that are greater than or equal to H, but less than N. And finally, the rightmost pointer would identify the path for values which are greater than or equal to n. As we access each node, comparisons against our target search value are performed to determine which path is followed as we navigate through the tree structure. Finally, when we reach a leaf block, we will either have found the key we're searching for, or if the key is not present, it means that record does not exist within the table. Because recall, all of the values within our indexed column will be present within this sequence set, the set of leaf blocks. So once we find the leaf block that contains the key, we take the adjacent pointer and then do another access to go directly into the table that contains the record with that key value. Before considering the access methods available through a B tree, let's recall the purpose of an index. First, an index can be used to provide an alternative path to data in the database. We could scan the entire table and examine every record to determine whether it satisfies our requirements. Alternatively, with the availability of an index, the index can be used to identify only the rows that meet our search criteria. Second, an index can be used to enforce an integrity constraint. Many relational systems use an index to enforce a uniqueness requirement. Such a requirement arises, for example, from a primary key, and also for alternate keys identified during database design. It's often the case that the column or columns over which an index has been created do not require uniqueness. In general, we can then distinguish between unique and non-unique indexes. Furthermore, recall from discussions of database design that we often wish to identify an atomic primary key, that is, a key that consists of a single column. However, there are times when the primary key will be composite, that is, it will consist of multiple columns. When a primary key is composite, foreign keys that reference this key will also be composite. Thus, in such situations, an index value will not consist of a single column or single value, but will be composite. When a query makes a reference to a column in a table over which there is a non-unique index, or the column serves as the leading or leftmost column of a composite index, a range scan can be used to examine the index. A range of values is selected from an index when an index range scan is performed. So a range scan results when we write a query where we use a greater than or a less than relational operator in our predicate. It also results from the use of the between keyword. Remember, that's equivalent to greater than equal and less than equal to values specified with the between expression. When we use pattern matching, and there's a trailing wildcard character, and also only the leading columns of a composite index are identified in the query. For example, if we have an index, say in our registration table, that consists of course number, section number, and student number, and the query specifies course number and section number, but makes no reference of a predicate involving student number, could trigger the use of a composite index on course number, section number, and student number. So let's consider how a range scan is performed. The index of the tree is entered through the root. The search proceeds from the root downward to the leaf node containing the first row included in the range. So if we have a predicate where some column is greater than some value, then we compare that value against what we find in the root node. Then we determine which vertical pointer will be followed as we move downward in the tree structure. Finally, we get to the leaf node where the key value would be found. So a horizontal scan of the leaf nodes is then performed, beginning with the block identified from that downward scan of the index. That is, we've identified the entry point into this double-linked list, this linear structure. Note that the keys in the leaf blocks are maintained in order. These blocks are also sometimes referred to as the sequence set of a B+ tree because the values are in order or in sequence. Another way that the system might use an index is referred to as a matching scan. When a query references a column over which there is a unique index, a matching scan, also called a unique scan, can be used to examine that index. For a unique scan, the index is entered again through the root, and the search proceeds downward from the root through the branch nodes until we reach the leaf node containing the key value that we are searching for. This sounds exactly the same as the range scan that we just described, and it does start off the same way. But the difference is that once we reach the node, we find a key with a single pointer. It points to, at most, one row in the table. If we do not find the key at all in this node, the row does not exist. But because there will be at most one row with this value, we don't scan. Once we've reached the leaf block through our vertical descent, we've determined the exact pointer value of the one row that contains the value. So we're done with the index. We then proceed to follow the pointer to the table. Our intention in the next few slides is to present kind of the natural or intuitive nature of query optimization. We'll be using a very simple table named Table X. This table consists of columns named K, A, B, C, and D, and column K is the key. So this is what the basic structure of the table will look like. We're going to be running this query, or at least discussing how this query would be processed by the query optimizer to produce an execution plan. The query says, let's select the values in columns A, B, and C from table X, where the predicate D equals 100 evaluates to true. So the purpose of these examples, once again, is to just show you the natural and intuitive nature of query optimization. It's now time to play optimizer. The optimizer does not execute the query. The optimizer determines the strategy for executing the query. That is, it produces the execution plan. Looking at the query that we wish to run, we said that we wanted to select some of the columns from table X, and the condition was such that D must be equal to 100. So the only information that we have about the table at the moment is there is an index on the primary key column, which is column K. So if you were the optimizer, what execution plan do you produce for this query? Well, the approach is to perform a table scan. Read every row in the table and check those rows one by one to see if they qualify. That is, does D equal 100? What's the rationale? Well, using the index and the primary key doesn't make any sense. It doesn't help us because the search condition makes no reference to column K, the column over which that unique index exists. The predicate is D is equal to 100. So therefore, we cannot make any use of the index on column K. We have to resort to a table scan. Second situation, slightly different set of circumstances. There's now a second index on the table. We have the unique index on the primary key, column K, and there is a non-unique index that has been created on column D. So this is a non-unique index. What does that mean? It means that any value stored in column D can appear in multiple rows. This is in contrast to the uniqueness of the index defined for the primary key, column K. Because column D has an index on it, the optimizer will likely be swayed to use that index to evaluate the predicate, D equals 100. It finds only those rows that satisfy this predicate and then accesses just those rows, not every row in the table. So the pointers that are obtained through the index, remember going back to that sequence set, the leaf blocks, these pointers can be used to access what we'll consider the matching rows in the table. More precisely, the way the index is used is it's a range scan because it's a non-unique index. Slightly different situation here. Again, we have the index on the primary key, column K, and that's a unique index. The index on column D in situation 3 is now a unique index. It makes a great deal of sense for the system to consider evaluating D equals 100, the predicate in the query, by using this unique index. The system recognizes that if it finds a match, it will find exactly one row. Because it's a unique index, at most one pointer will be found from the index, meaning at most one row accessed in the table. So the idea from these queries is, again, to show you the natural or intuitive nature of how query optimization works. Let's change the set of circumstances a bit. And suppose now we know a little bit more about table X than we did just a moment ago. Previously, we were talking about the presence of indexes. Now suppose we're informed that there are 100 rows in the table, and each row is approximately 40 bytes in length. Furthermore, the index has only one level. Going back to the B-tree structure, instead of having multiple levels from the root to the branching nodes to more branching nodes down to the leaf blocks, we see it's a much shorter index. Situation 1 once again says there is an index on the table's primary key, column K. How do we evaluate this? What is the execution plan? We again perform a table scan. Well, even though we know quite a bit more about the table, none of the information that we have about the table and the information about what the query's objective is, which columns need to be accessed, which rows need to be accessed, none of these things work together to allow us to use the only existing index. We must again resort to a table scan. Again, the index is on column K, and even though it's a unique index and it would be tempting to use it, it serves no purpose for us. There's no benefit. Change the situation again. Now we have column D with a non-unique index. This may surprise you. We perform a table scan even though there's an index on column D. Why would the optimizer resort to a table scan rather than use the index on column D? Well, it's that additional information that was made available to us. Each row is very short, and there's a relatively small number of rows. It turns out that with this relatively small number of short rows, not that many blocks are needed to store the entire table. These blocks can be obtained possibly with a single I/O operation, meaning that it's going to be fairly efficient to read that quantity of data rather than accessing the index, performing a couple of I/Os, and then performing an additional I/O, possibly many I/Os, to follow the pointers to the table. The idea is there's a reduction, potentially a sharp reduction in the number of I/O operations that need to be performed. Hence, the table scan works out to be more, say, persuasive to the optimizer. And finally, we change once again to having a unique index in column D. This time, it's quite likely that the optimizer says, I know that I'll get exactly one row, therefore it uses the index. Let's talk about this additional information and how it changed the decisions made by the query optimizer. The additional information told us how many rows were in the table and led to the number of blocks occupied on disk, the number of physical records for the table. The system could then justify quantitatively its decision to use an index or to do a table scan. In the previous situation, without the information about the description of the table quantity, number of rows, number of blocks, or the size of the index, the system simply took the route of saying, hey, I got an index, I'm going to use it. The opportunity presents itself, I'm going to use the index. That approach would be what is called rule-based optimization. The system was employing a heuristic, a rule of thumb. Think about that search that we talked about, looking in the database textbook for the material on query optimization. Have you ever looked in the index of a textbook for a piece of information, and then hopefully you'll find the page numbers that you wanted to retrieve the data from? Has the index ever failed you? That is, resorting to the index to try to reduce the amount of work turned out maybe there was no entry in the index. So the idea is there is no guarantee that using the index will improve the performance. But with a rule of thumb or a heuristic, the optimizer said, hey, indexes generally help me out. Using an index is generally a good idea. It improves performance. I'm going to go with my gut instinct and use the index. But with cost-based optimization, the optimizer doesn't go on a hunch, doesn't employ a heuristic. What it does is it can quantify its decision and say, if I use the index, it will cost me this much in terms of the number of I/O operations I need to perform. Whereas if I use a table scan, it will cost me this much in terms of the amount of I/O that I have to perform. So it had numbers to back up its decision. That's the idea of what cost-based optimization is about. Cost-based optimization is used by just about all commercial relational database systems today. Historically, not every database used cost-based optimization. Oracle database used rule-based optimization until finally around Oracle version 10, it said that's it. That's the end of the road for rule-based optimization. Now we're doing it entirely cost-based. Back in Release 7, Oracle supported both cost-based and rule-based. Now the cost-based optimization works if we have an accurate assessment, if we have good numbers in terms of the statistics, how many rows, how many blocks, what's the height of the index, how many leaf blocks, how broad or wide is the index, and so on. We'll talk about the need to gather the statistics and keep these up to date, reflective of what is currently in the database. We need our statistics to be current, up to date, reflective of the content of the database. Well, that's as far as we'll go for the moment. Let's recap what we've talked about. In this video, we discussed the B tree as a data structure. We said there were variations on this tree, such as a B plus tree or B star tree. The general idea of the B tree is it's a height balanced tree, and the B tree, or one of the family members, is used for indexes for operating system files and for databases. So we discussed the structure of a B tree and explained the access methods, how the index could be accessed using a matching scan or using a range scan. After that, we gave you a general feel for what query optimization is all about, talking first about the role of the query optimizer, and then we looked at rule-based optimization and distinguished that from cost-based optimization, recalling that we made the statement most commercial databases today use some form of cost-based optimization. So in the second part of this lecture, we'll look in more detail at cost-based optimization. We'll examine some of the statistics that are available in an Oracle database system, and we'll talk about the utility for gaining updated statistics. So we've got quite a bit still to cover in the topic of query optimization.